This is a video for AQA Discrete Mathematics. This is Game Theory section 1.3, where we're going to look at the optimal mixed strategies. Well, remember then from the last video that if we have the maxi-min is equal to the column mini-max, then we've got no stable solution, in which case the players have to consider what should be their strategy to maximize their gain. So therefore they have to vary and say not just play the play safe option all the time, but try and decide how often to play the other options. So player 1 would be thinking, well, how often should I play each of my strategies? And also player 2 should be saying the same thing. And then if they work this out correctly, what would be their maximum expected gain from this situation? So if we're in a situation where there's no stable solution, then the players need to consider their other options. And for a 2x2 game, we can look for an optimal mixed strategy by considering probabilities. So we say that let one of the players choose their first option with probability p and their second option therefore with probability 1 minus p. And then we say, well, if the other player plays each of their options, what would the gain be to player 1? And then having worked out the possible potentials, say what probability P would give us the maximum or the best possible outcome for the player. So here's a situation then where we've got the payoff matrix, and so we say let's assume player 1 plays strategy P with probability P. So this is going to be P and this 1 minus P. And then we can say from that, what's the probability player 1 chooses strategy Q? Obviously we just said 1 minus P. And from that we can say what's the expected payoff for player 1 if player 2 chooses X. So if we look down the column for X, we can see that the payoff will be 4 multiplied by P and then minus 2 multiplied by 1 minus P. So that becomes 6P minus 2. But that's if player 2 decides to choose X. What happens if they decide to choose Y? Well, there you can see we've got 0 times P and then plus 1 times 1 minus P. So that gives us a total of 1 minus P. We can represent those two possibilities on a graph. So you can see that our two expected gains are 6p minus 2 and 1 minus p for each of the different choices of x. We tend to do this on a graph where we've got probability on the horizontal axis, and then the vertical axis is the gain to player 1. Now, because probability goes from 0 to 1, it's easier if you put two vertical axes in, one at p equal to 0 and another one at p equal to 1. It then becomes very easy to draw these straight lines. So the first one, 6p minus 2, well, probability of 0 would mean that that starts at negative 2, and probability of 1 means it would finish at 4. So if you plot the start and finish points onto the graph, then it's very easy to draw the line. So this one, and then the second one, 1 minus p, starts at 1 and then comes down to 0. So remember then, this is showing us the gains for different values of p. So for example, let's say we chose a p here. Then if player 2 plays their first option of x, then the gain would be that value there, and in fact a loss to player 1. If player 2 chose the upper one, in other words y, then player 1 would gain. So the worst scenario for that particular value of p would be at this point here. Now remember that what player 1 is trying to do is to make that worst possible outcome as good as possible. So we want to actually move this value up, this bottom point on this graph, we want to move it up as high as we can. So that will bring us to this point here. So the play safe strategy for P is when P gives the biggest potential loss is as small, the potential loss is as small as possible. In other words, it's the highest point on the graph there, which is underneath all the lines. It's the intersection which is the highest point. And that means that if player 1 uses that particular probability, then their potential will be maximized. This point is the intersection of the two lines, so therefore we have that 6p minus 2 must be equal to 1 minus p, and therefore we get that 7p equals 3, p equals 3 over 7. The value of the gain, once we've got p is equal to 3 over 7, then we can simply substitute that into either of the lines. So using the line 1 minus p would give us a value to player 1 of being 4 over 7. So simply substituting the value 3 over 7. Now that was for a situation where we've got a 2 by 2 game, but we can use a similar idea if we've got a 2 by 3 game. So if there are more options for player 2. So we work in a similar sort of way. The fact that there are more options for player 2 really just means that we're going to have more lines on our graph. So we still let player 1 play P with probability P, and therefore Q with probability 1 minus P. And then we have different options. Firstly X, and so therefore we get minus 2P and 4 minus 1P. So that comes out to be 4 minus 6P. And then moving on to Y, you see that's minus P and 1 minus P. And that gives us 1 minus 2P in total. And finally for Z, we get minus 2 plus 5P. That comes from 3P and minus 2 times 1 minus P. So those now give us 3 lines which can go onto our graph. There's the first one, which I will then label as option X for player 2. The second one there, this is option Y. And then finally the third one, option Z. So X, Y and Z. Now remembering this idea that what needs to happen is that we need to maximize that potential gain. But let's just have a look at if probability is 0. You can see that the potential for loss is at minus 2 for player 1. So this minimum point on the graph is here, and we want to make that move upwards as far as we can. So what probability gives us our maximum on the graph? In other words, the highest intersection point. So once we've identified the point that we want to use on the graph, then we can get that by simply solving the two equations. So here we've got the intersection where we've got y and z, and so therefore we can solve the equation that 1 minus 2p is minus 2 plus 5p. That's straightforward, gives us 3 as 7p, and therefore the probability is 3 over 7. It's worth drawing your graphs reasonably accurately so that you can see whether you've got the correct value. We're saying that along the horizontal axis here, this point here is 3 over 7, and that looks about right on my graph. You can't read off the values from your graph. They're not going to be accurate enough. You're going to find the value using equations. However, it does help give you a little bit of confidence to know that you've got roughly the right answer on your graph. Once we've got the value of p, then we can say that player 1 is going to play that p with that probability, and therefore q with probability 1 minus that, which is 4/7. And then finally we can work out the value of the game by substituting p into the equation, either of the equations actually. So using 1 minus 2p gives us a value of the game equal to 1/7. So therefore we simply make the statement that the value of the game is 1 over 7. Well, that's player 1 sorted out, and we can see on the graph there that the value 3 over 7. What does this mean for player 2? Well, for player 2 has to be a little bit careful. You can see here that they shouldn't really play x at all, because x would potentially mean that player 1's gains are going to be even higher. So we can see from the graph that player 2 is not going to play x at all. And so, well, what value should they then play their other strategies, y and z? So a similar sort of argument says then, okay, let's let player 2 use strategy y with probability q, and strategy z therefore with probability 1 minus q. So we can say, what happens if player 1 uses p? So if 1 chooses p, then the gain is going to be equal to -1 times q plus 3 times 1 minus q. So this time we're looking along the row at these values, and that must give us the same value to the game of 1 over 7. So therefore we get that equation that minus q plus 3 times 1 minus q is equal to 1 over 7. That gives us 3 minus 4q is equal to 1 over 7, and therefore 4q is equal to 20 over 7, and q is therefore equal to 5 over 7. So player 2 should play y with probability 5 over 7, and therefore z with probability 2 over 7. So let's go through this again then, just very briefly as a summary. We check whether we can reduce the matrices for n by n gains, and with the questions that you will be faced then, yes, you'll either be able to get it to a 2 by n, so that player 1 has got 2 strategies, and we can solve it as we've just done in the examples. If we get an m by 2, in other words, we have a matrix which is the other way round, then it's possible simply to transpose the matrix and work as we've done. So we'll look at that. Here you can see that we've got a 3 by 2 game, and so simply by transposing this we can turn it into a 2 by 3 game from player 2's point of view. So to do the transpose, this time we're going to have player 1 on the top with their probabilities P, Q and R, and player 2 coming down the columns, 2 columns X and Y. Now from player 2's point of view, their potential gains are going to be the negative of the values that we have here. So if player 2 plays X and player 1 plays P, the gain to 2 is going to be 3. 1 is losing 3, therefore 2 gains 3. So we get 3, and then working down the column here and negating along the row of the transpose matrix, -1 and 4, and then 0, 1 and -1. So we've now turned this into a 2-by-3 game from player 2's point of view. So in summary, we should always first of all start off by checking whether there's a stable solution. But assuming there isn't, then we can determine the optimum strategy from probability equations and then graphing them. If we've got a 2-by-2 situation, then the intersection point tells us that we can then use that to work out the probability and therefore the value of the game. In a situation where we've got more than 2 choices for one of the players, then the player with 2 choices, we assign probabilities P and 1 minus P, and then look at the potential gains for each of the options for the other player. We then want to find the intersection point which is highest, and that will give us the 2 equations that we can solve for P. And then there will be one particular value which may not be used in some situations, and therefore you're going to ignore that one as a dominance argument has been used. Right, that ends the video on optimal mixed strategies, and indeed is the last video in the section for game theory.